Hello friends, in this video we are going to start with the microprocessor 8085 and we are going to discuss its basic features and the block diagram, or we can say the architecture of 8085. So let's start with our topic. The first microprocessor developed was 4004 and it is a 4-bit microprocessor. It was developed in 1971. After that, the 8080 microprocessor was developed. It was an 8-bit microprocessor. But this microprocessor has few instructions only and it can perform only certain operations only. So after it, another microprocessor 8085 was developed. It was the successor of this 8080 and it is also an 8-bit microprocessor. Now just let us study the basic features of this 8085 microprocessor. As you can see that it is a 4-bit microprocessor, so its first number is 4. This 8 is showing that it is an 8-bit microprocessor, and this 8 is also showing that it is an 8-bit microprocessor. So first feature of 8085 microprocessor is that it is an 8-bit general purpose microprocessor. It is a general purpose microprocessor, so it can be used in any type of application. Then it is a 40-pin IC. It comes in as a 40-pin IC package. This 5 in the 8085 microprocessor, it shows that it is using plus 5 volt power supply. It has an 8-bit data bus. It has a 16-bit address bus. So if we calculate 2 raised to the power 8, it comes out to be 256 bits. So it can have 256 bits of data, and 16-bit means 2 raised to the power 16, so it's come out to be 65536 bits. So it can address 65536 memory locations, and if we calculate it, it comes out to be 64 kilobyte. So the memory size of the 8085 microprocessor, it is 64 kilobyte. Then it runs at a maximum frequency of 3 megahertz. So these are the basic features of this 8085 microprocessor. Let us again study it. It is a 8-bit general purpose microprocessor. It comes as a 40-pin IC package. There are 40 pins in this IC and it uses plus 5 volts power supply. That is why it has the last digit as 5. Then it has a 8-bit data bus and 16-bit address bus is there. It runs at a maximum frequency of 3 megahertz. So these are the basic features of this 8085 microprocessor. Now let's come to the block diagram or the architecture of the 8085. This is the block diagram, or we can say the architecture of 8085. It is showing the various components or the various blocks of the microprocessor. The first block is the interrupt control, then we have accumulator, temporary register, serial input output control, instruction register, flag register, ALU, that is arithmetic and logic unit, then instruction decoder and machine cycle encoder, timing and control unit, then we have multiplexer. These are the various registers W, Z, B, C, D, E, H, L, stack pointer, program counter, then incremental, decremental address bus, address buffer and address data. So these are the various blocks or the various components of the 8085 microprocessor. These arrows, they are showing the various signals, and these lines connected between the various blocks, it is showing the connections or the buses which are providing the flow of the data between the various blocks. Here we have the various interrupts: INTR, INTA, RST 5.5, RST 6.5, 7.5 trap. Here we have the 8-bit data bus. It is the power supply. We have here the crystal is connected, X1 and X2, clock, general, clock out. These are the various timing and the control signals. Here we have the address buffer and the address and the data buses there. And here we also have the serial input output signals also. So let us study each of the block of this diagram one by one. First we will start with the arithmetic and the logic unit, ALU. The arithmetic and the logic unit, it performs the various arithmetic and logical operations like addition, subtraction, and logical operations like and, or. So all these arithmetic and logical operations, they are performed by this unit. Now these operations, the arithmetic and the logical operations, they are performed on the data. This data is provided to the ALU unit from the memory or from the input device. So it is going to fetch the data from the memory and the input devices. Then it is going to perform the arithmetic and the logical operations on that data, and the result which is obtained, it is going to be either displayed on the output device or it will be stored in the memory. If there is any intermediate result while performing these operations, then that intermediate result is stored in the temporary register. In 8085 microprocessor, we have a special register called accumulator, and this accumulator stores the data, and the result of the operations are also stored in the accumulator. So the ALU unit, it will perform the operations on the data from the memory and the accumulator, and the result of the operations, it is again stored in the accumulator. So let's study that what is an accumulator. It will be a special type of register, and this register is used to store the result of the operations, and it is a part of the ALU unit. It is an 8-bit register. So we have accumulator. It is an 8-bit register, so it can store or handle 8-bit data. It is designated or it is denoted by capital A. A denotes the accumulator. It is used to store the result of the operations. Now, in the microprocessor, there are various registers, and these registers are used to store or hold the data which is used in the operations. So here you can see that we have 6 registers B, C, D, E, H, L. These are the 6 8-bit registers, and they form the pairs B, C, D, E, H, L, forming a 16-bit register. If the microprocessor has to handle the 16-bit data, so it can use the pair of these registers B, C, D, E, and H, L. So if we talk about the registers in 8085, there are 6 registers. Also, accumulator is also a one type of register. So we have 6 registers, one accumulator. And also the 8085 has one flag register. Let's talk about the 6 registers. These 6 registers are B, C, D, E, H, and L. These are the 8-bit registers. And these 6 registers, they form 3 register pairs. BC, BE, and HL. These registers pair, they are used to handle 16-bit data. Now we have the accumulator. So accumulator, we have already studied that it is a 8-bit register which is used to store the result of the operations. Now the programmer, it can use these registers to copy or to move or to store the data, and using these registers, the microprocessor, it performs the various operations. So the programmer can use these registers to store or copy the data into the register by using the data copy instruction. Accumulator we have already studied. Then we have the flag register. The flag register, it consists of 5 flip-flops, or we can say there are 5 flags in the 8085 microprocessor. These 5 flip-flops, they are set or reset according to the operations performed on the data. That if we have performed the addition of two numbers and we have obtained a carry, then that flag will be set or reset. So we can say that these flip-flops, they are set or reset according to the result obtained after the operation. So the flags are set or reset after an operation according to the data condition of the result in the accumulator and the other registers. Suppose an operation has been performed and the data has been stored in the accumulator or the registers. So what is the condition of that register? According to that condition, the flags, they are set or reset. Set means either the flags are equals to 1 and reset means either they are equal to 0. So the 5 flip-flops or the 5 flags are, this flag register, it is an 8-bit registers. So let us divide the various bits. We have these are the 8 bits of the flag register, because flag register is an 8-bit register. These bits are D0, D1, D2. These are the 8 bits of the flag register, and we have here S, Z, AC, P, CY. These are the 5 flags. First is sign flag. Z is the 0 flag. AC is the auxiliary carry. P is for parity. And CY is for carry. So these are the 5 flags. Now let us study these flags. Sign flag means that whenever we have the 7th bit, because this 7th bit, the most significant bit of a number, it defines that whether the number is positive or negative. So when this sign flag or the 7th bit of the number, it is coming out to be 1, then this sign flag is set to 1, or it is set, that shows that this number is a negative number. And if it is 0, then the sign flag is reset, that is, it is make equal to 0. That means the number is a positive number. So first flag is sign flag. It is set if bit D7 of the result is equal to 1. And this is equal to 1, it means the number is a negative number. And reset if now next flag we have is the parity flag. The parity flag, it is set if the result has even number of ones. And it is reset if the result has odd number of ones. Next we have the 0 flag. Zero flag is set to 1 if the result is of the operation it is coming out to be 0. Otherwise it is reset. Next we have auxiliary carry flag. This auxiliary carry flag is set when a carry is generated from the bit D3 to bit D7. You can see in the flag register we have denoted this auxiliary carry flag at the D4 bit. So if from D3 to D4 a carry is generated, then this auxiliary carry flag it is set to 1. Now, when this condition arrives, because this condition it generally occurs when we have the BCD operations involved in the microprocessor. So this was the auxiliary carry flag. Then we have carry flag. If any arithmetic or logical operation it is generating a carry, then this carry flag is set to 1, otherwise it is reset. So these were the 5 flags used in the 8085 microprocessor. Now instead of these uh, flag register and accumulator and the 6 registers, there are 2 additional registers also in the 8085. These registers are 16-bit registers. The accumulator, flags and the 6 registers B, C, D, E and HL, these all are the 8-bit registers. There are 2 additional registers, 16-bit registers. They are the stack pointer and the program counter. Stack pointer is SP and program counter we can write it at PC. So let us study what is the use of these 2 registers. Program counter, it is used in the execution of the instructions. When the microprocessor it is executing an instruction, so the address of the next instruction it is stored in the program counter. Because the microprocessor don't know that where the instructions are written in the memory, the user it writes the program and store it in the memory at a specific location. The address of the first instruction it is given to the microprocessor, and the address of the second instruction will be stored in the program counter. So after the execution of first instruction, the microprocessor would know that the second instruction is stored in that location through this program counter. So the use of program counter, it deals with sequencing of the instruction. This register it is a memory register because it is pointing a memory location, and microprocessor uses this register to hold the address of the next instruction. Or we can say that the program counter it points to the memory location from which the next byte is to be fetched. Or we can say that when a byte is fetched by the microprocessor, the program counter it gets incremented and then it will point to the next instruction which has to be fetched. So if we have this as a memory location, and this is the program counter. First it is pointing at this memory location. First instruction is written here, then second instruction is written here. First the microprocessor it will fetch the first instruction, then decode it and execute it. Then this program counter it will be incremented by 1 and it is going to point at this memory location, so that after the execution of first instruction the microprocessor it will come back to this memory location. It will check the address from the program counter and will fetch the next instruction from this memory location. When this instruction has been fetched by the microprocessor, the program counter it is again incremented by 1 and then it will point to the next instruction. So in this way the microprocessor gets the memory location of the next instruction. So when a byte is fetched, the program counter it is automatically incremented and it is going to point the next memory location. The second 16-bit register is the stack pointer. It is a 16-bit memory register. It is also used to point the memory, hold the address of the memory location. So it is also called a memory register. As the name suggests that it is a stack pointer, so what it is going to point a memory location in the stack. Stack is what? It is an array of memory location. It is an array of memory locations. Suppose there are 10 memory locations, so that 10 array of the memory locations it will be called as a stack. And this stack pointer it is used to hold the address of the beginning of the stack, from where the stack is beginning. So it is the beginning of the stack So the beginning of the stack it is defined by loading that 16-bit memory address in the stack pointer. Suppose we have this. These are the memory locations in the microprocessor. It is an array and this array is starting from this memory location. Okay, so this memory location will be loaded in the stack pointer and that stack pointer will show that the stack is beginning from this memory locations. So these are the two 16-bit memory registers in the 8085. Next we have the instruction decoder. This instruction register or instruction decoder, it is an 8-bit register and it is used to temporarily store the current instruction which is being executed by the microprocessor. And the decoder, it is going to decode the instruction. What that instruction means, suppose we have written an instruction ADD. Now this instruction means that you have to perform the addition of two numbers. So this decoding of the instruction will be done in the instruction decoder. And then this decoded instruction, it is then passed to the next stage so that the microprocessor can understand that it has to perform the addition of the two numbers. It will start collecting or it will start reading the two numbers from the memory location. The next block of the 8085 architecture is the control unit. This control unit, it provides the timing and the control signals to the microprocessor so that microprocessor can understand that what operations and at what time it has to perform the operations. So this control unit, it is basically generating the signals on the data bus, address bus and the control bus within the microprocessor to carry out the instruction which has been decoded. Suppose again take the example of that ADD addition. So this will generate the signals that you have to collect the two numbers on which you have to perform the addition operation. Now comes to the buses, we have data bus, address bus and control bus. So how the buses are defined in the 8085 microprocessor. The 8085, it has 8-bit data bus and 16-bit address bus. So let us study the buses. First we have the data bus. The function of this data bus is to carry the data within the microprocessor. Whatever data has to be provided to the microprocessor, that data flows to this data bus. So this data bus, it is used to transmit the data, the result of the arithmetic and the logical operations. In the 8085 microprocessor, this data bit bus, it is an 8-bit data bus. It means that it can carry an 8-bit data, and this data bus, it is bidirectional. Bidirectional means that the flow of the data, it is in both ways, that is from the microprocessor to the memory and the input output devices the data can flow, and also from the input output devices and memory the data can come to the microprocessor. So we have, this is the microprocessor, we have memory and we have input output devices. So this data, it can come from memory or it can also come from input output devices, and the output or the result, it can go to the output devices also, and it can be stored in the memory also. So this dual flow of the data means the data bus, it is a bidirectional data bus, and it is an 8-bit data bus, so it is denoted like D0 to D7. D is for data and 0 to 7 are the 8 bits of the data lines. So you can say that 2 raised to the power 8, we have 256 locations. So 256 combinations of the data can be transmitted, and if there are larger numbers, then they have to be broken into 8 bits so that they can be transferred. First 8 bit of the data will be sent, and then second 8 bits of the data will be sent if it is a 16-bit number. So this is about the data bus. Then we have the address bus. This address bus, it carries the address of the memory locations. It is a 16-bit address bus. The 8085, it has 16-bit address bus, which is like starting from A0 to A15. These are the 16 bits of the address bus. A is for the address, and this is unidirectional. Unidirectional means that the address of the memory location or other devices like the input and the output devices, so the addresses, they can only come towards the microprocessor. The microprocessor is not going to send any of the address to the memory locations or any of the devices. Only their addresses can come towards the microprocessor. So this bus is an unidirectional bus. The flow of the address in one direction only. Now in this address bus, because we have here the data bus also and the address bus, so the lower order address bus we have from A0 to A7. This is called the lower order address bus, and from A8 to A15, this is called the higher order address bus. This lower order address bus, it is multiplexed with the data bus. D0 to D7. This is the data bus. So when they are multiplexed, it will become AD0 to AD7. A is for address, D is for data. So they are both multiplex. That is on the 8 lines, both the address and the data can be transferred. So the lower order address bus, it can also be used as the data bus. And the how the microprocessor, it is going to see that this is our address and this is the 8-bit data. This is done by demultiplexing the both the buses. So there is a buffer to demultiplex all this procedure we will study further in our videos. So you can see here that we have in 8085 microprocessor, the lower order address bus, it has been multiplexed with the data bus and it has become AD0 to AD7. The next we have the control bus. Bus, we have said that it is a group of lines or wires. So control bus, these are the various lines which provides the controlling and the timing signals to the microprocessor. So control bus, it provides the lines or the signals which have specific functions for coordinating and controlling the microprocessor operations. This control bus, it carries control signals which are partly bidirectional and partly unidirectional. Like some of the signals, they are unidirectional. They are going to be either coming out of the microprocessor or coming towards the microprocessor. And some of them are bidirectional. That is, microprocessor can also generate those signals and can also get those signals as an input. So let us study some of the status signals, controlling and the status signals which are used in the 8085 microprocessor. The first is ALE. This is an output signal, that is, it is coming out of the microprocessor. The full form of ALE is address latch enable. This ALE signal, it is used in the demultiplexing of the address and the data buses, and it is a pulse. It is a pulse which is provided when an address appears on the AD0 to AD7 lines. As I have said that on the 8 lines of the address bus, A0 to A7, the lower order address bus, it is multiplexed with the data bus. That is, on these 8 lines, both the address and the data can come. So the microprocessor will see this address latch enable signal. When it is 1, that is when this pulse is given, it means that AD0 to AD7, it has the address. Okay, and when it is 0, it means that data is available on that lines. So when ALE is 1, it means that address is available, and when ALE is 0, it means that data is available. Next signal is RD bar. RD and a bar on it. It is an active low signal. This bar shows that it is an active low signal. That means when this signal is 0, it means that this signal is active, and when it is 1, it means that this signal is inactive. Now this signal, when it is low, it means that the microprocessor, it is performing the reading operation. RD means read. So read operation has been performed when this signal is low. So this read signal indicates that data is being read from the selected input, output or memory device. Microprocessor is going to read the data from the input, output and the memory device, and then that data is available on the data bus. Next signal is the write signal. WR bar. This is also an active low signal. If there is a bar on any signal, it means that that signal is an active low signal. It means that it is active when its value is equals to 0. This write operation is similar to the read operation. When it is 0, it means that the microprocessor is performing the write operation. So when this write signal is low, it means that the data on the data bus has to be written on the selected input output device or the memory location. Next signal is input output or memory signal. Now this input output, it is an active high signal, and M bar, it is an active low signal. It means this is active when its value is equals to 1 and this is active when its value is equals to 0. So this is the input output and the memory operation. Now when the value of this signal it is 1, it means that the operation which is being performed by the microprocessor, it is an input output operation, and when its value is 0, it means the operation performed by the microprocessor, it is a memory operation. It is involving the memory, so this will be a memory operation. Next signals are the status signals. There are two status signals, S1 and S0. And the combination of these two signals, they define that what kind of operation is being currently performed by the microprocessor. So its combinations are S1 and S0, because there are two, so there can be four combinations of 0 and 1, 0, 0, 0, 1, 1, 0 and 1, 1. If the value of both the signals S1 and S0 is 0, then this is the halt state. 0, 1, then it will be the write state. These are the states of the microprocessor. 0, 1 means the write operation is being performed currently by the microprocessor. 1, 0 means it is a read operation, and 1, 1 means fetch operation. The instruction is being fetched by the microprocessor. So the condition of these two signals, the value of these two signals, either it is 0, 0, 0, 1, 1, 0 or 1, 1, it defines the state of the microprocessor. Now, according to the states and this, the various types of operations performed by the microprocessor are either it will be a memory read operation, memory write operation, or it can be an input output read or input output write operations. So there are four types of operations being performed by the microprocessor. So we have memory read, memory write, input output read and input output write. Memory read means the instructions, they are read from either the memory or input is read from the memory instructions or data. Similarly, input output read means instructions or data, they are read from input output devices. Memory write means the instructions or data they are write into the memory. And input output write means the instructions or data they are written into the input output devices. Because the result can only be given to the output devices, so this will mean that you have to write the data or send the output to the output devices. So these are basically the 4 operations performed by the microprocessor. So these 4 operations, memory read, memory write, input output read and input output write, they are performed by the 8085 using the 3 buses: address bus, control bus and the data bus. So we have the bus structure of the 8085 is like, this is the 8085 microprocessor. Then we have the address bus. Address bus is unidirectional. The address bus is unidirectional, so it has been shown in this direction coming out of the microprocessor, having 16-bit address bus, so starting from A0 to A15. This is our address bus. Now this address can be given to the memory, it can be the address of input or it can be the address of the output. The input is going to receive the input from the real world here, from outside world. The microprocessor is going to get the input and it is going to provide the output also to the real world. This is our data bus. Data bus is bidirectional. The data can flow in both the directions, into the microprocessor also and out of the microprocessor also. The input data, it is coming towards the microprocessor and the output data, it is going to the output devices. Also from the memory, the data can be taken by the microprocessor and also the result of the operations can be stored in the memory. So this is shown as a bidirectional arrow. The flow of the data between the microprocessor and memory is in both directions. This is a 8-bit, so starting from D0 to D7, 8-bit bidirectional data bus. This is our control bus. Control bus is again unidirectional and it is giving control signals to memory, to input and to output devices. So this complete diagram is showing the 8085 bus structure. Now again coming to the architecture of the 8085, we have this block diagram. So in this block diagram, we have studied the accumulator, we have studied about the flags and the arithmetic and the logical unit, the instruction register and instruction decoder and machine cycle encoder we have studied, timing and control unit we have studied that it is providing various signals, read, write, ALE, S0, S1 and input, output and M bar. Hold and HLDA, they are used in the interrupt signals. Reset in, reset out, they are used to reset the microprocessor, bringing it again to the initial conditions. This X1 and X2, it is providing the clock to the microprocessor, the clock signals, the plus 5 volts of voltage supply, it is connected here, and the crystal which is providing the 3 megahertz clock frequency, it is connected here. Then we have the 8-bit data bus, we have studied about it. Interrupts and serial input-output control, we will study in our later videos, that the microprocessor, what are the various types of interrupts in 8085 microprocessor, and what are the signals and how the microprocessor perform the serial input-output communication. Here we have the address buffer and address and data bus here. You can see that the higher order and lower order addresses bus, they are shown differently. Address buffer, here it is the 8-bit higher order bus starting from A8 to A15, and here we have the address and the data bus multiplexed with each other, AD0 to AD7. So this was the complete architecture of 8085 showing various blocks. Here if you divide this architecture, there are two parts, hardware and the programming part. Hardware model of the 8085, it shows the physical structure of 8085. What are the registers and the decoder encoders they are used. So this shows the hardware of the 8085, and the programming model, it shows the components of the 8085 which are used in writing the programs on the microprocessor. So this part, this BCDEHL stack pointers program counter, they deals with the programming part of 8085. So this represents the programming model of the 8085. So whenever hardware model is asked, then only shows this accumulator, flag register and ALU, and timing and control unit, buses you can show. So that comprises the hardware model, and programming model comprises the registers, stack pointer, program counter. This shows the programming model of 8085. So in this video, we have studied about the architecture of 8085. So I hope this video is clear to you. Thank you.